Lesson 211. So today we're going to move on further with logarithmic functions. Specifically today, you're going to look at the first time we've seen a log as a graph. And we're going to talk about some key features that come with a graph. How you get them from this type of equation, which we'll call the general form, where they come from and all that. But today's all about graphing. So some first basic principles here, or key characteristics. When we evaluate a log, there's a few values that cannot be zero. Just plain and simple can't be zero, otherwise it's not a log anymore. For example, if a is zero, what's zero times anything? Zero. That would all cancel out, the log is gone. So a cannot be zero, and this also tells you b cannot be zero either. So a and b both cannot be zero. That's your first blank to fill in right there. Zero, there it is. Okay, so now with the base, our base has to be a positive value. You cannot have a negative base. So n has to be greater than zero, but there's one value that the base cannot be. Do y'all remember what the value was? Think of exponentials. Remember inverses? Exponentials and logarithms are inverses of each other. What was the one base that an exponential could not be? Wasn't negative. They have to be positives, but there's one positive value it cannot be. I'll give you a hint. It's in between what would make it a growth or a decay. 1. The number was 1. You can't be 1 because you have to be either growing or decaying, and so 1 would be a line. So you need to have a different value than 1. Okay, what we're going to learn today is the domain of, well, the range is always going to be negative infinity to positive infinity. I'll show you that as we go. The domain will not be. Their domain will have a restriction. The graph will only exist on a certain value. Now, typically, it's going to be 0 to infinity. So I'm going to put up here typically. What does typically mean? Does it mean always? No, what is typically usually? I escaped away. Typically means usually. Usually we're going to go from 0 to infinity, but we'll always know it's based off this value of c here. This says x minus c. That's just because x's, are they truth tellers or liars? They're liars. That's why it says minus c. But as far as the domain goes, it'll be the positives of it. So it'll be once you take away the lie to infinity. That's going to be the true form of the equation. Now, let's talk about growth and decay. Just like exponentials, exponentials could be growing, exponentials could be decaying. The same is true with logarithms. If a log is increasing its growth, there's 2 ways to make that happen. One, the easiest way, which is most common. Here, I'll put most common here. Most common is that a is greater than 0 and your base is greater than 1. That would make you have a growth. If your a value is positive and your base is greater than 1, you're growing. One that's less common, but still could exist, is if a is less than 0, meaning a is negative, but the base is in between 0 and 1. This is not that common, so I'll put uncommon here. This is uncommon, but still mathematically it can occur. Those are your 2 ways to have growth. Now, let me just simplify everything for you. If a graph is logarithmic growth, what does that mean is happening to the graph itself? It's doing what? It's growing. It's increasing. Okay, let's go to logarithmic decay. If a log is decreasing, the most common way that you might see it is, well, I don't actually know. This might be the most common. I don't know which one of these is more common, so I won't make a mark on that. Is that a could be less than 0, meaning negative, and base greater than 1, or that a is greater than 0, but your base is in between 0 and 1. And I don't know which one of these is more common, but either way, if it's decaying, it's decreasing. Okay, let me make sure you caught what's most important for you right now. If a function is growing, if a log is growing, what does that mean the graph's actually doing? Increasing. If it's decaying, what does that mean it's happening? Decreasing. Good. The graph will only increase or only decrease. That's what this is saying right here. Logarithmic functions are always increasing or they are always decreasing. They never change directions, ever. They're either increasing or they're decreasing. They are never changing directions. And that's the next blank. They never change direction. Because they never change direction, they should not have any extrema. What is that word extrema? What did that mean? Like a minimum. A minimum or a maximum. Since it's always either increasing or decreasing, You don't have a minimum or a maximum. Even on the end where you start from, it would go down forever and the other end goes up forever. That's why there's never a minimum or a maximum unless you have a restriction on the graph. So I'll put arrows on this so you can see it goes higher and higher and higher. There's never a maximum point. To have a maximum, it has to be a point. And the same for a minimum. Those are arrows, they go on forever. That's why there's no maximum. Okay, finally, last little note here on concavity. Concave up versus concave down. Remember, this just means the graph is curving up or the graph is curving down. Check out this first picture. Which way is it curving? I know it's increasing. Don't say it's increasing. Which way is it curving? Is it curving upward or downward? It's actually curving not upward, but downward. Logarithmic functions are always concave up or always concave down, meaning they're always curving one direction. This one's curving downward, where this one would be curving upward. I know it's decreasing. It's a little tricky at first, but you can see that it's bending more and more like it's trying to turn positive. They never change concavities. We never change directions. Because of that, you'd have no points of inflection, no inflection points. An inflection point means you're changing your concavity. You're changing which way your graph is curving. Okay, that's the front little page of characteristics. The characteristics that you really need to know are really these 4 boxes. As time goes on, you need to start recognizing these 4 boxes. Today, it's a lot to ask to get you have these 2 down today, but we do need to know this. A log will always either be increasing or decreasing, and it'll always be concave up or concave down. All right, the next slide, there was just a few more of these I couldn't fit in. I copied and pasted the first box. So again, if you wanted to look at the equation, there it is. You have your vertical asymptote. The graph will approach some value of x. We'll see today. You can find your x-intercept or y or other key points using these values. I'm going to copy and paste this one later today. I don't think you have to have these memorized. If you do, it'll only be like one problem. We're just going to not worry about that. We're going to put our mental power somewhere else. Today, I will use the calculator when it comes to graphing, but then I'll show you using this formula how you could have found the points. Finally, what you do need to know is about the limits. So remember how I told you there are 2 types of logs. There's a log growth and a log decay. Whoops, chose the wrong line there. This one says, let's talk about growth first. If a log is growing, what that means is you start from some value, usually the y-axis, and it curves this direction. That's what it's going to look like. Now, in this particular case, this value right here is represented by c. So I'm going to put x equals c, a vertical line right here. I'm going to call it x equals c so that if you look back in your notes, you understand what this is talking about. As this graph goes left, does this graph go left forever? No. What value is it getting stopped at? C. This is saying C. Do you remember what the plus meant? Give you a hint. Did not mean positive. It meant something else. It means it's on the right side of C. So if this is C, the dashed line, is the graph actually on top of this dashed line? No. It's to a side. Which side is it on? The left side or the right side? Right. Because it's on the right, that's a plus. That's what that means. Now, this is asking us to find a limit. Remember, a limit doesn't tell us where the graph is, but it tells us where the graph is going. Where's this graph going as you get closer and closer to C? Where's the graph going as you get closer and closer to C? Is it rising, falling, getting flat, or stopping at a point? It's falling. So if it's falling, you put in, what symbol represents falling? Negative infinity. Okay, and what happens as we go right forever? This means there's nothing to stop us. So as we go further and further right, what's happening? It's rising to infinity. Now, if it were decay, I'm going to go over here and add just a quick little sketch. If it were decay, it would look like this. Graph would be decreasing. Once again, you'd have an asymptote. At C, I'll call it x equals C. Okay, so this is now the limits for decay. What happens as we get closer and closer to C? Is the graph rising, falling, getting flat, or stopping at a point? It's rising. So what symbol means rising? Positive infinity. And then what's happening on the other end of the log? As we go right forever, the graph is falling forever. What symbol means falling? Okay, check out the two limits. These are how your limits will look on every single logarithm. What do you notice you have as your two answers? A negative and a positive infinity on growth. What about on decay? A positive and negative. You're going to have the same answers, just a matter of which to order. For a logarithm, it's always going to be, the limit will always have a positive and a negative infinity. Always. Make sense? Okay, what will every logarithm limit have? One positive and one negative. That's because the graph's always either increasing from negative infinity to positive infinity, or it's decreasing from positive infinity to negative infinity. That's why you always have that. Okay, with all that, you ready to get started? I'll come back later and I'm going to copy and paste this little section in a moment. But until we get there, let's start with this graph. The first one, it says write limit statements for the end behavior of the following log graph. Now, what did we just say is going to be true of every single log we look at today for the limits?
There will be a negative.
There will be one positive and there will be one negative. Okay. On this first graph, when you look at it, there is a asymptote. The asymptote means it's an area the graph is approaching. It doesn't tell us what x value is that graph approaching. Like what value of x would this be if it's right on top of the y-axis? 0. Put x equals 0 here. This graph is approaching 0 on the left side. And on the right side, there's nothing, no bounds. It's going to go forever. So let's write our limits. This first limit right here, I'm going to put LIM. We call this function f of x. And then you put an x with an arrow. Okay, first tell me, what x value is this graph approaching as we're going to the left? As we move left, does this go left forever to negative infinity? No, there's something stopping it. What value is stopping it? The 0. Now, if you're ever on the x putting in a number, you need to put a plus or a minus. We're not on top of 0. Are we on the right side of 0 or the left side of 0? The right. So you put a plus. You're on the right side of 0. That's what that plus means on a limit. You're on the right side of 0. Now, what's happening to my graph as I go to the left? Is it rising, falling, getting flat, or stopping at a point? Nope. As you go left, it's falling. What symbol means falling? Negative infinity. Okay, now tell me about this limit over here, this arrow. Let me write it out. LIM f of x equals x arrow. Okay, what value of x am I approaching if there's no bound as I move to the right? Positive infinity. It's going to positive infinity. Tell me about my y's. Wait for more people. What y value is it approaching? Positive infinity. It's rising. There's no other bounds on a logarithmic graph. Okay? So now let's look at part B. Let's look at this one. Now tell me, my base, excuse me, that's not my base. That's my a value. Is my a value greater than 0 or less than 0? A is greater than 0. If a is equal to 2 and that's greater than 0. Now tell me about my base of 1/3. You compare it to 1. Is that bigger than 1 or less than 1? It's less than 1. So what I'm going to be looking for is I'm going to go to my notes section, see what happens when my a is greater than 0, but my base is in between 0 and 1. So let's go find out what happens when your a, it's on this slide, two pages before, your a is greater than 0, but your base is in between 0 and 1. Logarithmic growth, which one? The most common or the uncommon? Most common, a is greater than 0 and the base is greater than 1. Is that what we had? No, try again. This one, a is less than 0 and base is in between 0 and 1. No, our a was, it's logarithmic decay. Which one, top or bottom? It's this situation right there. What was our a value again? 2, and our base was 1/3. We're going to use that formula right there. Or not that formula, this situation. It's logarithmic decay. So let's come to our picture, and we're quickly going to sketch a logarithmic decaying graph. So it doesn't have to be a brilliant graph. Just quickly, let's get something on there for our notes. There's my x and y axis. I'm going to put y equals g of x. Okay, this is a logarithmic decay, we said. So if it's a decay, we need to have a graph that decreases as we go from the left to the right. Like that. How many limits would I need to draw for this graph? 2 limits. I have 2 arrows, 2 ending values. I need to draw 2 limits. By the way, this asymptote would be at x equals 0. X equals 0 is that asymptote. Okay, our first limit, this limit up here. This time the function is called g of x, so I'd say limit g of x equals, and then x arrow underneath. This graph here, does it go left forever to negative infinity? No, it's getting restricted by some value. What value is stopping it? 0. Okay. Is my graph on the left side or the right side of 0? Because anytime x is going to a numerical value, you have to put a plus or minus. It's on the right side, so you put a plus. Now, what's happening as this graph approaches this value of 0? As I get closer and closer to 0, what's happening to it? It's rising. So what represents rising? Positive infinity. Very good. Now, what happens as I go to the right? It decreases. Okay. So if it decreases as I go to the right, and there's no bound on going to the right, so it's just an infinity. You don't have to do a plus or minus on infinity. That means you go forever. You only do that when it's a numerical value like 1 or 2 or something like that, or in this case, 0. You said it decreases. It falls. My graph does not rise. It does not stop at a value. It does not get flat. So it falls. What symbol represents falling? Negative infinity. Okay, one more time. What has to be true for every single graph, every single log graph's limits? One's positive, one's negative. You're going to have some x value with a number and a plus or a minus, and then one infinity, plus or minus infinity. Positive or negative infinity, I should say. That's going to be the same true over here. So you will have a numerical value, but it'll be an x value. Okay? That's what's true for logarithms. Now, with that, I want you to go to the back of the packet and try number 2. DOL number 2. All right, now example 2. We're going to look at the same 2 graphs we had a moment ago. Same 2 equations. This time we're going to talk about if it's increasing, decreasing, or concave up / concave down. This first graph of f, remember we had this one earlier, we said it was exponential growth. I don't know if you remember that. We said it was growth when we wrote the limits. Why would this be growth? The graph is increasing. That's the first thing they want us to identify. Is it increasing or decreasing? The answer is this is increasing. Now, which way is the graph actually curving? Is it curving more and more upward, or is it curving more and more downward? The curve is changing to where it's a downward curve. So does that mean it's concave up or concave down? Concave down. This is concave down. Now, I want to remind you of a definition. If something is concave down, what that means is happening is that this graph is a decreasing rate. So since it's increasing, this graph would be increasing at a decreasing rate. Now, what's this? These are putting these 2 together. Because the graph was increasing, the graph is increasing, it's going up. It is increasing from right here. It's increasing, but concave down would mean it's happening at a decreasing rate. So that comes up here in a little bit, but that's like the definition. Concave down, describing concave down using English words would be to say that the rate is decreasing. Does that make sense? It says, so is it actually increasing or is it decreasing? Which one's happening? It's increasing, but the amount it's increasing by is slowing down. Does that follow? It's not increasing by as much later on as it was earlier on in the graph. Okay, let's look at the next one. This one, do you remember what this graph looked like from last example? It was decay. Good. Let's go ahead and put a decay graph on there. We said it looked like this earlier when we wrote our limits. And I'm going to put a G on there. So there's our decay graph, logarithmic decay. This is in fact decay. Okay, so tell me, is this graph increasing or decreasing? Decreasing. This graph is decreasing. Now let's talk about, is it concave up or concave down? It's curving upward, so this is concave up. When you put these two statements together, if you put these two statements together, we would say this graph is decreasing at an increasing rate. Decreasing at an increasing rate when you put those together. Now, why I'm writing it this way, you're about to see on number 1. I want you to go to the back of your packet, and I want you to try DOL number 1 on the back. So go try DOL number 1 on the back of your packet now. Now we're going to take a look at example 3 here, and we're going to look at some tables. So we saw some tables in previous classes. Do you remember if a function is a logarithmic function? If a function is a logarithmic function, do you remember what that meant about the table, how it was going to be laid out?
X's are proportional.
X's would be proportional or geometric, and the Y's? Arithmetic or equal length adding, yeah. Okay, so let's just walk through how we would solve for problems in the table, okay? Here, what is my change of y? How much is my y changing by every time? 1, okay. Since we're talking a lot about equations, here, first go ahead on your notes, put that's delta y equals 1. If you were writing an equation in general form, let me put it up how I had it earlier. If you were writing, whoops, I called this an N on this one so I could use B, C, and D inside. If you were writing your equation in general form, the delta y, that is your A value. So A would equal 1, okay? That is equal to your A. Just so you know, if you're writing an equation, that's how you get that. Now come over to our x's. Are our x's changing the same way? Does it look like it's counting by ones? 1, 2, 3, 4, 5. Would that be changing by ones? No. So if it's changing differently, what I would suggest you do is you have your arrows. From 1 to 2, how much do I increase by? 1. From 2 to k, I don't know. You could put a question mark if you wanted to. And from k to 8, we don't know that value either. How about from 8 to 16? Do we know that amount? That's changing by 8. Now, here's the deal. What we can say is it's not the same number. So this first column, this must not be arithmetic. This must be geometric. I'm going to go ahead and put that line down that this must be geometric. Arithmetic would mean it's adding or subtracting by the same amount. And I can see that it's not. This, however, is arithmetic because it's the same number all the way down. Is everybody with me so far? Now, what we learned on the last couple lessons is, your last lesson in particular, that your base, it's going to be any two, you could take any two change of values and that are back to back and divide them to find your change. Now, I don't have any values that are back to back, so I must use this column instead. So here's what I'm trying to say for the formula. Your base is equal to delta x2 over delta x1. That's what we try to use. But if those values are not available, then you just have to do x2 divided by x1. Otherwise, you can't get your answer. So on this particular problem, let's take our base and divide our two closest x's. These are my two closest x's. What's 2 divided by 1? Okay, so what does that mean? That means each one of these change of values is going to get multiplied by 2. So this next one would be plus 1 times 2. What's plus 1 times 2? No, plus 1 times 2. There you go. The value after would be a plus 2 times 2. What's 2 times? And to check it, that would be, you take the 4, and if you multiply that by 2, do we get plus 8? Yeah, we do. So that means I need to add 2 from here to here. I'm adding 2. What's 2 plus? This k would be 2 plus 2. What's 2 plus 2? 4. That's k. K is 4. That's our answer. That's our answer on this problem. K is 4. And not only is k 4, since there didn't seem to be any other transformations, I'm going to go ahead and tell you the equation would look like this. F of x would equal 1 log. What did we say our base was? Nope. Base was 2. And then you would have x here. And if you plugged in a 1, it should be a 0. Okay, your x would be like this. You don't know about the d, but there will be a d value in this one. And in particular, the value would be 1. That's just some extra information, but that would actually be your equation this time. This d value, you don't know yet, so you could just leave it as a d. But on this particular problem, d would be 1. D would actually equal 1, but I'm not solving for that here. Those would be the a and the b, though. That's where I'd get those values. Okay, let's go to our next problem. On our next problem, I might need some more space, so I'm going to just kind of move this out of the way here. On our next problem, tell me what you notice looking at the problem right away. What's the easiest thing to stand out to you? What's going by 5s? The y column. Okay, put over here that our change of y, or delta y, is equal to 5. And that 5 value would represent a. Good. If you had to write an equation, which we don't on this one. Since these are changing by 5s, that means this column is arithmetic. Good. This one is arithmetic. Whoops, got dyslexic. Okay, so now let's look at these values. Do these appear to be adding by the same amount every time? So we can go ahead and guess that this is going to be geometric. And by the way, that's the definition of a logarithm. A logarithm has x values that are geometric or proportional, whereas the y's are arithmetic, or adding an equal length value each time. Now, so what we do is, since it's changing, I'm going to do a change of again column. This one, we don't know how much it's changing by yet, but I do know how much it changes by going from 7 to 19. How much of a change is that? That's a change of 12. Do plus 12. Does anybody know? Mental math chance here. From 19 to 55. Is it just Giovanni? The value is 36. And there's one more. I can tell it's going to be over 100. How much over 100 will it be? 108. Good. Now these are geometric. If you want to know your base, I would take this blue formula right here. If possible, if you have back-to-back change of values, use this formula. That is the delta x2 over delta x1. That's the better base formula to use. In this particular problem, my second base is 36. My first one is 12. What's 36 divided by 12? 3. That's my base. My base is 3. That means each one of these is getting multiplied by 3 each time. Yep.
What is the x2 and x over 1?
Over here, I did not have back-to-back and the change of columns. I didn't have like an x2 and x1. This is like an x1, delta x1. This is delta x2, delta x3. That's delta x4. You see how there's a gap? Because there was a gap, I couldn't use that formula. I had to just do x2 over x1. But this one, there's no gap. You see how these are back-to-back? meaning there's no question mark in between, I can just use those, and that's a better formula to use. That's my base. My base is 3. So to solve this one, I'm actually going to go backwards. If the base is 3, that means it was the question mark times 3 to get to 12. Does that make sense? Question mark times 3 gave me 12 because the base is 3. So another way of doing this is you could take your 12 and divide it by 3. What is that 12 divided by 3 going to equal? That means this was a plus 4. Now, if this was a plus 4, then that means k plus 4 is 7. That would mean that k plus 4 equaled 7. Then, therefore, k is 3. Now, that's the answer to this problem. If you wanted to write the equation, here's what we know so far. You would say that f of x, not f of x, sorry, this is called g of x, would equal, what's my a value? 5 log. That's my a value, 5. What was my base? 3. This one, the value's been shifted. If this k is a 3, this should not have been a 3. It needed to be a 1. Your first value needs to be 1, 0. So this one's too large. You need to make it x minus 2. That's how my equation would look. Right there, I believe if you plugged in points, 3 minus 2 is 1, 0. Oh, and a minus 5 on the outside. Now, these two values, that's the c and the d. You don't actually have to solve for those. So what I'm actually going to do is I'm going to do a c minus d, and then we'll just plug it in. So for the sake of your notes, just go ahead and do minus c, and then here plus d. What we'd find out is that my c value itself, c is 2, because I would need to subtract 2, and then my d on this one is a positive 5. You don't need to know those by hand. I'm just giving them to you. I want you to know, though, how the a and the b play together in the equation. That's what I want you to know. Go ahead. Okay, so the equation's extra stuff today, especially the c and d. I could tell, knowing that my base is 3, these should all be multiples of 3. You see how that's a 3? Does 3 to some power give you 7 and then 19? No, it goes 3. It'll be like 1, 3, 9, 27. Those are the numbers I'm looking for. These needed to be a little bit larger. 1, 5. Actually, that's not, I needed to go not larger. Let me think here. 3, I might have had this backwards. If I took away 1, that's a 1, that would work. But taking away 2 is a 5, that does not work. I might need to think for a second what I'm doing wrong here. I would be looking for 1, 3, 9, 27. Okay, something's off in this part. I'm not going to put C. I'm glad y'all said that. I don't know what they are. We're just going to leave it like this. Because you don't have to know what they are. And I'm not figuring it out off the top of my head anyway. So I'll just leave it like that. That's the part of the equation you would need to know. Whoops. Okay. I've done 2. I'm going to do 2 more. And I'm going to get away from the extra stuff. On C, tell me what's happening on C. What do you notice looking at that right away? Okay, you see there's exponents. Good.
X is.
I'm
sorry, that's Y.
That's Y. The Y, how much is the Y changing by every time? And that means that is arithmetic. Good. Okay. On the X column, am I adding a certain amount every time?
No.
What seems like it's changing? The power's changing. So I don't know how to represent this by arrows because I'm not adding a certain amount. I'm multiplying a certain amount. I want you to think of this. This might help you out. E to the power of -2. A negative power means it's in the denominator. That means it's like E times E in the denominator. Does that make sense? Well, this value would just be E. This one we don't know. E to the 7th would be like E times E times E times E times E times E times E. 1, 2, 3, 4, 5, 6, 7. Okay. And then finally, e to the 10th. Okay. There's 10 of them there. How much am I getting multiplied by every time here? This is geometric. It is getting multiplied. What am I multiplying by every time? And here 3. I'm not actually multiplying by the number 3. What are we multiplying by every time?
3.
Where every time it's getting multiplied by 3e. So I want to put here the base is the same thing as e times e times e. Now what's another way of writing that? We're multiplying by e cubed every time. Now this is a tricky problem, but we're multiplying by e cubed. Let's check it out. If I multiply this first one by e cubed, would that give me this value? If I took e cubed and multiplied it by this, what would happen first? These two, they would cancel with 2 of those, and what are you left with? E to the first power, okay? And then if I multiplied that by 3 e's, I would now be taking e cubed times e to the first, and what would we get here? E to the 4th power. If I took e to the 4th and multiplied it by e cubed, what do I now get? E to the 7th. Is it working? Yeah. K on this problem is e to the 4th. The part of the problem, as far as writing an equation goes, that I want you to know is that h of x would equal what's my a value? So it'd be 7 log, and then you'd have a base of e cubed. I'm just going to leave it like that. That would be my equation. Now, I want to do one more with you before I give you one to try. All right? Kevin, what do you notice when you look at this column here? It's decreasing by how much? It's decreasing by 1, which that is our a value. Would we call this arithmetic or geometric? Miguel, if it's always adding, or in this case, always subtracting, do you call it arithmetic or geometric? Arithmetic. Put arithmetic there. This is arithmetic. Okay, let's look at the x column. Sorry, the x column. Do I seem to be adding by the same amount every time? Yes or no? What do you think? No. So if it's not adding by the same amount, it's not arithmetic. What are we going to call it instead? This is geometric or proportional. You could use that word as well. Okay, let's talk about how much it's changing by. How much do I change going from a -7 to a -4? I increase by 3. How about from -4 to 8? Nope. From -4 to +8. 12? Do we know how much we increase from 8 to k? Okay, we don't know. Do we know from k to 248? No, but we can figure it out. Do we have back-to-back values here? We can solve for our base then. The base would equal +12 divided by +3. What's +12 divided by +3? 4. That means each time it's getting multiplied by 4. Now that I know that, I can find this question mark. This would be +12 times 4. What is +12 times 4? +48. So k is going to equal, k will equal 8 plus 48. K will equal 8 plus 48. What is 8 plus 48? 56. That's our answer here. If I wanted to make sure this is accurate, you could check this one. You would take 48 and you'd multiply that times 4. Plus 48 times 4 is 192. And if you did 56 plus 192, you do in fact get 248. That 56 plus 192 is 248. So we did do it correctly. Okay. Last thing before I move on from here. If you're going to write an equation, they call this m of x. If you're going to write an equation, the two things that are important, you need to know the a value. What's our a value on this problem? Any more people, please? What's my a value? -1. You don't have to put the -1, but you do have to put the negative. Log, what was my base? 4. And then you'd have x minus c and plus d on the outside. That's how the equation would be built. But we're not focusing on the c or d yet. Okay, you've seen me do the important things here. If possible, do a change of. This column I couldn't do a change of on, but always look to do that and then find out your values. I want you to try this DOL, okay? We're going to call this DOL number 3. But I want you to try this one right here, okay? From here on, the rest of example 4, here's what we're going to do. We're going to graph this in the calculator to have an idea what the picture should look like. And then I'm going to show you using one little box from the characteristics on how you could mathematically find the points if you got in a weird situation that you need to. I don't think you're going to have to do this by hand, but just in case. The one thing I know you need to know by hand is this, whether or not it's growth or decay. When you look at this base, does this base look like it should be growth or should be decay? It should be growth. There's only one thing you need to now check. It looks like 3 since base is greater than 1. The one thing you need to check, let me say base, which equals 3, is greater than 1. The one thing you need to check is my a value here greater than 0 or less than 0. Since a is greater than 0, it's straightforward, and it's just based off the base. This should be a growth graph. Make sense? Don't graph like I'm about to do. We know it should look like this. Don't actually do that in your paper. We're going to be more exact. That's what it should look like, okay? We all tracking? Okay, now what I'm going to do instead is we're going to go to our calculator. And I want to make sure we know how to look for it and everything else. Go to your calculator, hit new document, don't save, and I want to go to graphs. We're going to graph it. It was 2 log, that's control 10 to the power of x. Our base is 3. And then it was x on the inside. Hit enter. Are you getting this graph? Okay, what I want you to know is every logarithm is going to have an asymptote. On this particular case, where does it appear the asymptote is? I'm going to add that in. Let's see, graph entry. I hear 0. Which variable? The x value of 0 or the y value of 0? I'm going to type in x equals 0 and you'll see it. Does this graph seem to be approaching this red line? Or does it cross it? It's just approaching it. That's right. So this is my graph. We have it right there. That's x equals 0. Okay, and I'm going to paste this over, and then we'll plot some points here. Do you have an x-intercept here? Where do you see the x-intercept? At 1. So go over here, put 1, 0. Look at the value when x is 2. What does it look like the y might be? 1. So when we're at 2, it looks like the y value is 1. Actually, how about this? Press Control T over here. That was better. Let's hit Control T. It's not 2, 1. Where should the next point be? 3, 2. Okay, let's plot that point on there. Okay, so I plotted that one in the wrong spot. This one needed to be at 3. 1, 2, 3, up 2. And the next point, if you go back to your table, where's the next good point for us? 9, 4. And I'm going to show you why that's the case. It'll make, hopefully, some good sense to you in a second. So 9 is going to be just off, but it'll be up at 4. And I'm going to see if you can notice the pattern. So this one, this point was 1, 0. This point was 3, 2. This point was 9, 4. Now the reason why this graph looks like this It's going to be because your x's get multiplied by some value, your y's get added by some value. Look at your equation. What's the y's going to be added by? That's going to be your delta y. Remember that? That's your delta y. Delta y is equal to 2. Every y value should be changing by 2. You see how it has a y value of 0, then 2, then 4. You see how that works? But what does it mean if your base is 3? You multiply by 3. So what's 1 times 3? 3. What's 3 times 3? 9. So what would our next point be if we were going to extend our graph? 27, comma 6. Very good. Are you tracking with that, Larry? Why would the next point be 27, comma 6? Because it's a negative? Try again. Why would the next point be 27, comma 6? What's the pattern? Oh, okay. I had to change it to a relation to get x equals 0. So I went menu graph entry, and then I did x equals 0. The reason is because definition of logarithms, x's multiply, y's add. The base is what you multiply by. We multiply by 3. So 1 times 3 is 3, 3 times 3 is 9. 9 times 3 would be 27. Then you'd multiply 27 times 3 and so on, get 81. The a value is how much you're changing by. The rule of logarithms is that the y's add or subtract. In this case, they add by 2. Does that make sense? Larry, does that make sense to you now? Okay, let me go back all the way up here to this slide. I said earlier I was going to come back to it. Define your key points. This slide right here is the math that we're following. If you were doing algebra, which I don't know if you have to do this by algebra, but this is the slide that I would be using. Transformations are when we have a number on the those that C and D I was talking about. That's when I would say transformations. This one doesn't have much of transformations. So the way you do it is your n is your base. And so if your power, let's just say we plugged in a 0, what's anything to the 0 power? So you see how P is like my power? What does P stand for in this problem? Say power. Power. If you plugged in a power of 0, what's 3 to the power of 0? 1. And then if you plugged in a power of 1, what's 3 to the power of 1? 3. So it would be at 3, 1. This one's at 3, 2 though, because our a value is 2. There's actually a transformation. So you could use this if you want to use algebra. I don't think you have to, so I'm not going to spend that much time on it. Does that make sense? But that's how you can do that using algebra. All right, let's go to the next one. I want you, before we graph it, let's talk about it. What should this one be based off the base? Growth or decay? This should be growth. You would think it would be growth. Since your base is 2, which is greater than 1, you'd think it's growth. Is it actually going to be growth? No. What's it going to be instead? Decay. Since a is less than 0, it becomes decay. So this graph is actually going to decrease.
So they both have.
So if your a is positive, you just go off the base. If your a is negative, it's going to be a liar. It's going to just go the other way. It'll be the opposite of what you would naturally think. Okay, it's that simple. No crazy rules with it. This one, we will not have an asymptote at 0. There's a shift. Do y'all remember our transformation rules? Do x's lie or tell the truth? So we're going to shift which way? Shift 3 units right. And so this one, what we're going to find out, does not have an asymptote at 0. It's going to have an asymptote at 3. I'm going to go ahead and add that on my graph first. This one was going to have an asymptote at 3. And we said it's going to be a decaying graph. Okay, let's go graph it and we'll copy it over in a second. Okay, so let me take this away. We'll get the table in a second. Our equation is, what's the negative number in the front? Negative 5. Log was our base at 2. And then it was x minus 3. That part I remember. And I'm going to change my asymptote from 0 to a 3. I hit table. What's up? Sure. Okay, by the way, you can tell where the asymptote is. Look at this. Where there's not an asymptote, it says error. Where the asymptote is located, you get the undefined. That's the asymptote at 3. But then here's our good points. I'm gonna come here where I can get, looks like 3 good points. 4, 0, 5, -5, 7, 10. Let's get that on our note packet, those points. So I'm gonna plot that in right here. So the first point it says is good is 4, 0. 5, -5. 5. This is 4, 0. 4, 0. 5, -1, 2, 3, 4, 5. 5, -5. And then finally, it says at 7, -10. 5, 6, 7. -10 is somewhere down here. I'm going to just place it right there. That is 7, -10. Okay, looking at the points, what can you tell me is happening with the y's? They're decreasing by how much? 5. Is that a surprise to us? No, because up here the delta y is -5. Okay, now my x values, this is what looks a little different. They don't look like they're getting multiplied by 2, do they? It's because of the shift. How much of a shift did I start off with? 3. If you take away 3 from each of those, they would be multiplied by 5. Watch it. Take away 3. What's 4 minus 3? 1. If you multiplied the 1 by the base of 2, you would get a 2, right? Well, how do we get 5? 5 is, if you take 5 and take away 3, what do you get? 2. Notice it's 2 units away. That was 1, 2 units away. Okay, what's 2 times 2? 4. So the next point, if this one was 1 point from the asymptote, the next one's 2. The next one would be 4 units from the asymptote because that's what's getting multiplied by every time. See, that's why it's 7, 10. It just looks weird because of that transformation right there. Okay, all that stuff is calculator stuff. You don't have to know that by hand. At least I don't think you do. So I'm going to leave it like that. I'm not going to stress this out. Trying to figure out stuff you won't ever have to know by hand. Whoops. Come on, draw. Hey, before we forget, would we say this is increasing or decreasing? Decreasing. Is it decreasing at an increasing rate or decreasing at a decreasing rate based off its concavity? Decreasing at an increasing rate because it's concavity. This function is, we said this is decreasing. We said it's concave up. Therefore, this function is decreasing at an increasing rate. I didn't do that in the last one, probably should have. Yeah, let's go ahead and just add that note while we're right here. Let's take a look at the last one. Would we say this is an increasing or decreasing function? Increasing function. Is it concave up or concave down? Concave down, good, it's curving downward. Therefore,
The increase.
the function is increasing at a decreasing rate. Why was it decreasing with a... Great question. So this one, you go off the base, and if the base is greater than 1, it should be growth. If it's less than 1, it should be decay. Unless the A is negative. If the A is negative, then it changes it. Okay, this one, the base was 2, which made us think growth, but because of the -5, it became decay. Let me put this out. I like the way I did it a second ago. I think it looks better. Okay. I can't remember. Do I have 4 graphs what we were doing? Okay, let's take a look at the next one. what do you need to know by hand? You need to know a couple things by hand. Number one, do you assume this is growth or decay when you see the base is? You say it's decay. Now we need to check that. Okay, we need to check that. You check it by looking at the A value. The A, is it greater than 0 or less than 0? If it's greater than 0, I make no changes. So this is decay. You need to know that by hand. It's going to be decay. The other thing you would need to know is the shift. This does have transformations, and so what you would do is 3x plus 1. Our graph has to be, for the asymptote, you set it equal to 0. I think I'm supposed to be doing domain range on this. I think I've been forgetting to do that. This graph will have an asymptote whenever this equals 0. That's where the asymptote would be. So let's just solve it to find out which way it would be shifted. What would be the first thing you would do to solve this?
Okay.
You would subtract 1 from both sides. So 3x would equal a negative 1. And then finally, divide by 3. We will find out in a moment that their asymptote is going to be at x equals negative 1/3. We will confirm this in the calculator, but x equals negative 1/3 is where we should have an asymptote, something like that. This graph is decay, so it should be going down this way, like that. I think those are all the pieces you need to know by hand. I should have been doing domain and range, so I'm going to go ahead and just include that up here. The domain, how far left? I can state how far left will this graph travel? Negative 1/3, and it's going to go forever right. Do you remember what the range will always be for a log? Negative infinity to positive infinity. Okay, so now let's go graph this and we'll get the exact points. So come to your calculator. This equation was, what number was my A? 4. The base was 1/2. 1/2. And it was 3x plus 1. Okay. 3x plus 1. We hit enter. I told you that this base would be different. It is. I mean, the asymptote. Where's our asymptote? Negative 1/3. What do you think? Does that look like the correct asymptote? All right, great. That's going to be our graph. I'm going to hit Control T to get a table. Do you see any good points on there? Oh. It looks like starting at 0, 0 is a good point, and there's only a couple of them. So we'll take what they give us. You said there's one more good point? Oh, 5, negative 16? Yeah, that one's way down there, isn't it? Okay, so we'll just stay right here. Here's our good points that we're going to be using. Let's plot 0, 0. We'll plot 0, 0, and we'll plot 1 to the right, down 8. That's right there. What did we say the next one would be? 5, negative 16. I could put that on my table right up there if we wanted to. Oops. That would be my next good point. But I ran out of space. So let's go ahead and connect the dots. Okay, tell me. Increasing, decreasing? Decreasing. I'll give you a chance to write, catch up. Okay, you said this graph is decreasing. This graph is decreasing. Whoops. This is decreasing. Concave up or concave down? Concave up. Therefore, this function decreasing at an increasing rate. That would be how you'd put that together. I forgot to put these points on there. 1, -8. There we go. All right. I hate to go out of order. I'm gonna go back though and add in the domain range of this one. How far left does this graph travel? How far left would this graph travel?
3.
No, how far left?
2.
To 3. How far right does it travel? Infinity. And what is every single range of every single logarithm function? That's right. Unless the graph gets cut off by a restriction, like let's say tell you to cut it off, it's going to be negative infinity to positive infinity. Okay, and I didn't do this one either. How about this one's domain and range? How far left? 0. This is stuff you need to know by the without the calculator. From 0 to infinity, and what's the range always going to be? Positive infinity. There you go. All right, I think I had one more. All right, let's talk about this one. So this time I want to make sure we get everything we need to know without calculator. We get it all together this time. I want to do my job right. Tell me about my base. Growth or decay?
Okay.
It looks like it's going to be decay when you start. Why does it look like it's decay? Because your base is less than 1. But there's something else we need to check. Okay, if your A value is -1, that means A is less than 0. Will it still be decay then? What's it now become? It's going to be growth. So this graph will look like growth. Because when A is less than 0, it goes backwards. Okay, let's talk about the asymptote. What type of shift do we have this time?
It goes right. The right. And up to.
And we will go up 2 units, but I'm going to put the asymptote on first. So the asymptote is usually at 0. This one's going to be shifted over to the right 3 units. Are we all okay with that one? This will shift it up 2 units, but that doesn't matter on the asymptote. That doesn't actually matter on the asymptote. Going up, it's a vertical line. That doesn't matter if you shift it up. You can't even see the difference. Okay, we're going to graph this and then go get some good points for it. Let's go to our calculator. It was a negative in the front. Negative in the front. Negative log with the base of 1/3. This was x minus 3. And then we had a +2 on the outside. Hit enter. Where do we think our asymptote should be? Do you remember where we said we thought the asymptote should be?
3.
3. That is in fact correct. The asymptote is at 3. All right. If I hit Control T, I should get a table. What good points are y'all seeing? Yep, the asymptote is in fact at 3. That's where it says undefined. 4, 2, and 6, 3 are good points. And 12, 4 would be another good point. So it takes a while to get there. I'll leave it right there. So 12, 4 would be the next good point. If you want to add that in, well, I'll do it right here. If I wanted to add that in, 12, 4 would be the next good point. Okay, so I'm plotting at 4, 2. 1, 2, 3, 4, up 2. 6, 3. 1, 2, 3, 4, 5, 6. 1, 2, 3. And 12, 4. Well, that doesn't make it on there. All right. Now that I've walked you through that, we need to do domain range. How far left did our graph travel? 3. The domain would be from 3. How far right does it travel? Infinity. The domain will always look like that from the asymptote to infinity. And then what's the range always going to be for a log function? Negative infinity to positive infinity. Okay, are y'all ready for this? Oh, sorry, one more thing. Increasing, decreasing. This graph is increasing. Concave up or concave down? Is it curving up or curving down? Okay, so it's concave down. Therefore, when you put those together, the function is increasing at a decreasing rate. Okay. Do you know how else we could write this? Well, I want you to count it out. Let's see what the base, how we could have thought about this. This function, does it actually look like it's going down by a unit every time? It doesn't look like it's going down. It actually goes up 1 unit. Now, look at the values. This is 1 greater than the asymptote. How many points is this greater than the asymptote? 3. The next point would be at 12. Remember, the asymptote is at 3. How many bigger is 12 than 3? No, not 8. Try again. How many bigger from 3 is 12? 9. So notice this is 1 bigger, 3 bigger, 9 bigger. What's happening every time? It's multiplying by 3. Did you know, this is kind of putting it together here, that you could actually write your equation as if you have a negative and a base that's a fraction, if you remember your exponents, you could turn this positive and take the reciprocal of the base. And you have the same exact graph. Did you know you could do that? If your base is negative, you can take the reciprocal of the base. And work that way. Okay, that would be true on all the other ones. Do we have another negative base earlier? Yeah, here. What's another way we could have rewritten g of x? 5 log 1/2 base of x minus 3. You could have done the same thing there as well. Okay, now I wouldn't have done it here because I like my base to be greater than 1. I think it's just easier. But that's what you can do. Or this one, for example, you could rewrite h. You see how I have a base of 1/2? If you so desired, you could rewrite this as -4 log with the base of, since I made the 4 negative, I take the reciprocal of my base. 2 to the 3x plus 1. You can do it that way as well. All right. Last thing you got to do, try DOL number 3 and then submit your answers online. That's it. So DOL number 3. Once you finish number 3, go ahead, scan this QR code and upload your questions there to College Board.